Hi everyone, I'm Junyi from Facebook, now known as Meta, working as production engineer for Meta. Today we're going to talk about data correctness at scale and how do we guarantee data correctness in your production system. Quick overview again for the agenda. We'll first go through the concept, explain why we think correctness is important, and then we'll go through the details in regarding how do we implement consistency check toolings, and then how do we apply those implementation of correctness checks in production system. And then in the end, we went through a couple of different war stories and shared that experience that we learned from production and testing environment regarding like how do we see issues can occur in terms of data correctness issues. So first, concept and context. What is data correctness? So data correctness in a very abstracted way, it's our expectation regarding the asset property that normally a relational database would provide. MySQL itself is an implementation of a traditional relational database, so we would expect it also provide this full set of ACID guarantees as it was deployed in production. If that's still too abstracted, here's a list of kind of concrete examples of how do we expect correctness can be presented and guaranteed by a relational database implementation such as MySQL. So some obvious things, we don't want a database to kind of persist a partial commit on some of the record replicas, so that is like a basic expectation for integrity. And then also via crash recovery, we want to know zero data loss, and then that guarantees the durability of the database systems. And then obviously MySQL is known very popular. It's a very popular database that utilize replication as a way to fan out data. So we want to make sure like all the different instances are serving the exactly same copy of data instead of like inconsistency being observed in a production deployment system. Similarly, MySQL using different B trees to store the extra data and indexes. So we want to make sure the consistency between different B trees for the same table are also presenting the same copy of data. More on top of that, we can also expect consistency across different systems. For example, we take logical backups from online database every day. We also want to make sure like the backups we take every day is also consistent with the online data, so which is what we call the cross-system consistency expectations. So why are we doing this, or why in the world do we care about this? Hopefully I don't need to explain this to everyone sitting here, and then it's so natural for everyone. But again, like just for the context, why do we care about correctness and how this can go around? Obviously, automation is the most fast changing part in our production environment. Although we do also change the code and logics in the MySQL server ourselves as well. But automations get deployed more frequently. What we call is control plane, and then they deal with all the shard migrations across different replica sets, and also deal with promotions when random failures occurs in production deployment. So these are the things that are very crucial to the production data and deal with data directly, which is why any change on top of those toolings might have implication on the correctness of the data. So we want to make sure like all the changes that we make to those toolings don't end up causing correctness or inconsistency issues in production. Other than that, hardware failure is kind of common thing when you deploy large-scale machines in production. Bit flip can happen everywhere. We're seeing bit flip from disks, memory, CPUs. Whenever there's a data copy between different components in the system, it can be like cross host or within the host between different components, a bit flip can happen. Unless you implement a fully end-to-end checksums outside of the box and treat the machine as a black box, this is not preventable. So basically, bit flip can happen everywhere. So even a checksum on the physical data is not trustworthy because you might end up already corrupting data before you compute the checksums and then persist the raw checksum to the disk, and then this whole thing like it just doesn't give us guarantee for the full end-to-end consistency. Other than that, like what I mentioned, basically maintain a branch of the MySQL code base so we maintain our own fork of MySQL and then deploy Facebook specific features on top of that branch So we're also making a lot of changes to MySQL Server, which is why we also want to make sure like the new changes or the new features we add to the server itself doesn't end up corrupting data, and then guarantee consistency. So all in all, these are the reasons that why we think we need correctness, because these parts can possibly go wrong in production environment. So then implementation for the actual tooling is that checks for the data consistencies. So before we talk about the actual tooling, first clear out some terminology. So we're on the same page regarding the different names of the system. So MySQL in Facebook use semi-sync replication. Which is pretty standard setups. We have primary, multiple secondaries. For the illustration purpose, I will just draw 3 instances here. So individual one of them coming together form this replication topology, which we call a replica set. And then all the instances within that replica set will serve the exactly same copy of data. And then for each individual replica, we refer this as, they're normally referred as instance or replica. And then in Facebook, we have a multi-tenant deployment environment. So basically, instance from different replica set can be co-located on the same physical host, which is what we normally call a host or a physical machine. So now that we're clear about the terminologies, next is how do we check consistencies? So all the consistency check toolings was built on top of this assumption that if we can align 2 different logical data sets on the same GTID, which represent the state of the data set, right? So if they are on the same state, then we would assume the checksum or the fingerprint value that computed from those 2 data sets should be identical or look exactly the same. So this kind of particular statement will be served as a kind of baseline for all the consistent implementation further on. So as we can notice, we highlight 2 building pieces here. If we can somehow align the GTIDs for 2 different physical data set or logical data set, then we can build checksum mechanism on top of that to check consistency. So next I'm going to explain how do we achieve the purpose of GTID alignment for MySQL instance, and then how do we compute checksums for the data that was stored in the MySQL instance. First, GTID alignment between different MySQL instances. As you may have known, we deployed 5.6 everywhere in Facebook at this point, and then everything used GTID natively. So therefore, we rely heavily on GTID for most of those consistency checks. So how do we kind of create snapshots on different instances that are taking this update from asynchronous replication and making sure they are on the exactly same state, whereby we can expect the consistency to be kind of observed. So first, I guess I would just go to the animation for better illustration. So here we have a 3 instance deployment replica set, and then say we want to make sure we're about to check the consistency between 2 secondaries. Then we need to open 2 consistent snapshots on top of those 2 instances to serve as a base for the consistency check. So here we can see secondaries keep taking update or DMLs from the current primary. So at any given point of time, it's totally possible or reasonable to assume that they're on different pace of the replication, they're on different GTID set. So here, first thing, we'll just pick a random secondary from the pair, stop the replication there, so that the data on the picked secondary becomes stale, and then it's not taking any DMLs from primary. So at this point, it's not moving along with the GTIDs. And then secondary at this point, the other secondary at this point has already moved forward. So it has more GTID, which is on position 3. So on this live secondaries, we then issue a statement called start transaction with consistent snapshot. It will start a transaction which will then provide a isolated view within this connections. So then all the data within the snapshot becomes stale, and then it's not impacted by any upcoming update or emails coming from the primary through the replication streams. So now we have a snapshot that is stale and consistent from the left end. And then we'll resume the replication by use a very specific syntax here, start replication until GTID. And then the GTID here will be the GTID that we observed from the snapshot that we just captured from the left hand. So that after executing the statement, the replication will just go through as normal, but it will stop itself until the point that we specified. So basically, it will keep replicating, catch up to the point to GTID4, and then the replication will stop by itself. At this point, secondary on the right is still stale, not taking DMLs, but then we can safely assume that the data observed from this secondary now is also persisted at this particular GTID set. So then we start and snapshot using start transaction, which is the same statement that we used on the left hand secondary. Now we have both snapshot open for these two different instances, which presumably should give us exactly the same copy of data between those two instances. So that serves as a common ground for the next step, which is checksum calculation. And yeah, more importantly, after all these, we resume the replication for the secondary on the right hand, so that all the production traffic and reads can still read the most up-to-date state of the data to serve the online traffic. All these happens in a sub-second granularity, so there is very limited kind of impact to the production system when going through this whole logical flows. Question?
How often is it on some set interval, or is this just randomly done across the fleet of record sets?
Yeah. So the question for the live stream, we're gonna repeat it again. How often does that operation happens in production, right? So there will be a slide further down explaining how do we do this at scale. But in terms of frequency, we try to make sure that we cover the consistency across the whole fleet within a month or a couple of weeks time frame. So depends on the deployment size. Then yeah. So basically, I would say on the magnitude of a couple of minutes or hours, this will happen to some of the replicants.
Yeah.
Cool. Move forward with checksum. So now that we have two consistent snapshots where we can compare the data, obviously the most straightforward way is just to fetch all the data from those two instances to the client side and compare them one by one, which obviously is not efficient, which is also very error prone because then we need to deal with all the kind of encoding issues on the client side. And then most of the automations was written in Python in Facebook. Therefore, Python itself is not is kind of notoriously inefficient when you have large scale of data. So obviously, we don't want to have all the comparison done on the client side, which is why we came up with this approach that we use checksum to represent the state of the data, so that we can simply compare the checksum and they have all the heavy lifting jobs done on the server side, and then simplify the comparison logic on the client side. Other than that, we also want the checksum mechanism to provide a couple more features. For example, it should be accurate. The checksum shouldn't have any side effect of false positive or false negative. It also needs to be efficient so that we have a precise granularity control and the pacing control over how fast it can exhaust the production resources when the checksums are being computed. Also, we want to be able to utilize exactly the same mechanism to pinpoint the drift once the inconsistency was identified. Because what we want to know is not just whether or not these two data sets are different, but more importantly, like how they look different and what exactly look different. And then that will serve as important evidence to figure out the root cause of those data drift once they are identified. So that sort of already explained the question you might have already had in mind. Why in the world are we re-implement the wheel while there's already tooling sort of cover this area like PT table checksums and checksum table. None of them cover all the aspects that we're looking for here. For example, PT table checksum is replication intrusive. It also create triggers in replication stream and sort of exhaust the kind of precious replication throughput in the system. So it's not entirely read-only, while our tooling wanted to be kind of non-replication intrusive and also purely read-only from operational perspective. Similarly for checksum, the granularity is on the table boundary. So we don't really have any resource control mechanism over how fast it can compute the checksum and how many CPU and compute resources when the command was fired against the instance. And also, it only tells whether or not these two tables look different or not. And then it will left to the operator to figure out what exactly is different once you know the checksum looks different. So with all that said, we implement our own tools for both consistent check and also identify the drifter once the consistency was identified. So the logic for the checksum is pretty simple. It's actually quite similar to what PD table checksum was using, with slightly different tweaks that was made in logic. So for illustration purpose, here what's presented is a single table with two rows. So the goal for the checksum is basically compile a sort of fingerprint-like value for the table that can represent the state of all the values that were stored in the table. So first thing we'll do, we use concat with separator to connect all the columns for every single rows together. So as the output of this step, you will see every single row have their columns squashed into a single string. And then on top of that, we'll run CRC32 for each individual row, compile a fingerprint value for each individual row. And then next up, we will use bit operation to squash all the rows into one single value. So that, in the end, becomes a fingerprint value for the table and all the data in the table. Just to make it more shiny and look like a checksum, we convert this from a decimal into hex code. But that's super optional, just to make it professional. So in the end, we get a checksum for the table. That's how the SQL cross will look like for a checksum statement running against the Masco instance. So that simplified version of checksum does come with some caveat. So we made a couple of iterations and improved the SQL statement to make it more resilient to false negatives. False negatives means when you have actual data inconsistency, but the checksum report exactly the same value for these two different data sets. So one possible false negative here is that concat with separator, we just clearly ignore all the none values on the table. So here we can see two different tables, while the none value was persisted on different columns of the row. But as the output of concat with separators, the output look exactly the same because they just discard the none values for all the same, all value remaining together. So to work around the issues, apart from concatenating all the values from the row, we also compile a sort of bit mask for all the number values and representing the sequence of how and whether they're actually none persist for this particular row. So with those information connected to the actual values with the row, we make them look different when this exactly same case happening. So you can see the 1, 0 on the top row indicates that the first column, the first nullable column was actually none, while the second column wasn't. On the opposite side, the second row then tells us the first column is not none, and the second column is nullable. And then obviously with the concat string being different, the checksum computed against that is also different. So you might ask, why don't we just wrap around all the columns with if none and then convert to some not nullable value and sort of work around this issue? So that come at a caveat that whatever value that we picked for the conversion might have a conflict with the actual production data. So we can never guess like what are the values that can observed in the production system, which is why we don't try to guess a sort of unique value for the conversion, but rather use a bit mask strategy to work around with all the nullable values. So here's just an example like how these wouldn't work out if we use if none wrapper for the column. That if you use 1 as the output to convert the none value, then it might collide with the actual 1 value that is persisting in production. So whatever value you choose, there's always a chance that production data also contain this value, and then end up with a false negative situation. So just a quick recap on all the things that we mentioned and how we can use these building pieces to compare checksums and detect correctness issues across different instances in the same replica set. So say here we want to check the pair. The picked pair here is a primary instance and a secondary index. We first create two consistent snapshots on top of those two instances, and then run a SQL to compile the fingerprint of the data stored in the instance for each individual table, then compare the result, and then come up with a conclusion that whether or not these two instances are consistent with each other or not. So going back a little bit to provide more concrete answering regarding like why are we not using checksum table, one of the reasons that I mentioned that it doesn't give you the answer what exactly is different. It only tells you that those two tables are different. So to be able to use the logic that we just mentioned and then apply to the same kind of drift detection requirement, we just go through this simple example to illustrate how do we use the same logics to detect the actual row that are different. So here, assume we have two tables, and they're on the same GTID set, but one of them has the value persist to be A, which is correct. The other table is sort of corrupted or bit flipped, or for whatever reason, is stored a different value, which is round, which is C. And then the checksum tells us that those two tables look different. So how do we know that, let's say ID, the primary key here is ID. So how do we tell that the primary key equals to 1 is the actual drift? So here we used the similar mechanism. Instead of using binary search, we basically just break the table into multiple chunks with a predetermined chunk size. And then using the same SQL similar SQL to compile checksum for individual chunks. So we narrow down the data drift into a range where it can be represented by a where clause with a static size. So here, for simplicity, I choose the chunk size to be 2 rows. So basically, after the table is detected to be inconsistent across instances, we just go chunk by chunk for this particular table, start from the very beginning using a cursor mechanism. If you're familiar with online schema change, this is how basically it breaks the table into smaller chunks. So you use this kind of SQL sugar to record the last rows into the session variable, and which will be used as a cursor for this kind of chunk-based checksum mechanism. So here, first chunk will be the first 2 rows in the order of primary key. Compute the checksum, they look identical, which is correct, we move on. And then iterate on different chunks until the first chunk that has checksum compiled to be different, so that we know this particular chunk looks different. And then we'll pinpoint then we'll try to narrow down the exact row. The logic is still the same. So we now know the exact range of data where the data inconsistent was persisted. So we just go row by row using the same SQL, but using limit 1 this time instead to identify the actual differences. So we scan from the very beginning of the chunk and then till the end, till the point where we found the data inconsistency. So now we know this particular row, which has ID equals to 10,001, has a different values for the same column, which is what break the consistency check. So that particular mechanism that I just mentioned come with obviously a lot of issues, and we've made a couple of improvements on top of those logics to make it play more nicely with the production environment. So in ODB, as we may have known, that it's kind of vulnerable to long snapshot, which is exactly what the consistency check will cause. So sometimes with heavy workload, we observe long history lengths and then sort of have a standard herding problem to the production system when a long checksum query was running against the instance. So we made some trade-offs in terms of consistent guarantee and the actual production impact, so that we start to break this snapshot into smaller pieces and only guarantee consistency within a certain boundary. For example, The snapshot boundary can be a list of tables, or it can be a single table, or in worst case, it can be a range of the table. Depends on how long the checksum will be taken against this selected chunk of data. So what we're using here, initially we're using kind of re-snapshot with a certain cumulative size at table boundary. So whenever we check, like say, 10 gigabyte worth of tables, we reset the snapshot so that we release the cursor from high history length and allow the purge to purge the ODC entry, so that we don't end up accumulate too much stale purge data in the purge log. And later on, we found this still has issues because people tend to create large tables, sometimes terabyte worth. So a single select can take multiple hours to finish. So resetting snapshot at table boundary still doesn't help in these cases. So we end up introducing a history length watchdog that's setting aside, keep pulling the size of the history length. If it goes beyond point, it will just kill the current running checksum query and then start to break into multiple chunks as a trade-off to avoid this causing production impact while still provide consistency checks to a certain limit. Other than that, to avoid impact on production system, we realized the actual execution thread and then avoid peak time for the checksum to further reduce the impact from production system. So with all that said, there's also other issues that the logic that I mentioned still have a possible case where we see false negatives because the usage of bit or. So for example, if you have a table that have only one single row, while on the other hand, you have another table that has exactly the same row but repeated 3 times. So with the bit or, you end up having two exactly the same checksum, which is a false negative case. But this was an issue in Facebook deployment because as a part of the 8.0 migrations, my colleague will have a talk tomorrow about 8.0 migration in general. But as a part of the 8.0 migrations, we have one of the prerequisite of the migration was to convert all the replicas to be RBR, role-based replication based. So therefore, for role-based replication, we enforce all the tables to have at least one unique constraint. So with that said, we will never have duplicate rows in the table, which is sort of a way to work around these issues for that particular logic. So with all that said, we have trade-offs improvements made for these issues with only one issue that still unaddressed, which is how do we cover the short limit drift? Because we use replication, and then we also use RBI everywhere, which is known to sort of cover or paper over the short limit drift by just modifying the data. And then for Facebook, this is more of the case because you have lots of live usage of the data and then all the rows that sort of being updated all the time. So whenever you have a new version of the row that going through the replication through RBR, then you sort of resync the data if there was an inconsistency before. So for these kind of short limit drift, there isn't a really good way to identify those inconsistencies if they ever have an inconsistency. Because as I mentioned for the other question you asked before, that we only guarantee the completeness of the coverage for the fleet for a certain period, which is normally on the magnitude of weeks or months. So which is why we don't really have a good coverage for short limit drift. So to fight against that issues, we also introduced a live consistency check at the part of the replication, which utilize the role-based replication. And the DBA might have hit this annoying issues in similar ways before, that your replication was broken with duplicate key error or key not found when replicating RBI events. So the idea there is pretty much the same, but it's a expansion on top of that logic. So instead of only checking the primary key values when we're executing those RBI events, we actually compared the full pre-image that was persisted in the binary logs against all the columns and values for the corresponding rows and the instance that the events was executing against. Question?
So on that, can you use row image minimal still, or do you have to use row image rule for replication on row is?
So the question is, for this particular type of check, do we use a minimal binlog image? So that's a good question. We actually implement a new binlog image mode for us to to only persist pre-image for all the columns while only persist the columns that have been changed in the after image. So it's sort of a trade-off. There is still increase in the size in terms of the pre-image because we need to record all the rows for the consistency check. But we try to avoid duplication in the binlogs for the after image.
Okay.
Yeah, and maybe I should have shown this earlier, which answers the question. So here, as an example, we have two tables. The ones on the secondary has a corruption. There's supposed to be a zoo value for the name column, but it end up with a bar. So how do we identify the issue with the consistency checking replication? So for RBR, the events will be roughly look like this. On the primary, when the update was executed against the table, updating the value from full to zoo as a part of the DML. So with traditional replication, this will just silently happen in our replica, override the round value bar into zoo, which resync the drift and then make the inconsistency disappear. So with the live correctness check, when running this particular update events, it will, like I mentioned, it will use all the pre-image value to match against the current row on the replica. And then it will found, okay, we expect to see full for column 2, but we end up seeing column value bar. So that will bump a counter and record exactly differences for pre-image and observed value in performance schema. And then we'll raise alarm to the operator to investigate the issues once this happened or captured by the replication stream. So now that we've covered all the building pieces for consistency check, we'll then explain how we apply this consistency check at scale with large deployment. Quick recap on the basic assumptions. Now we have the capability of aligning GTIDs and the checksum computed from those two different data sets should look identical. So if we're being creative about how do we define those two data sets, the same mechanisms can be used for a lot of different places to guarantee consistencies. So depending on how do we choose the data set on the AB side, we'll be able to achieve these correctness guarantees for these scenarios. Steady state, we have lots of replica sets, so we want to make sure every single instance in the replica set looks like the same. Also, we're doing a lot of migrations, sometimes going from 5.6 to 8.0, sometimes going across engines from InnoDB to RocksDB. Sometimes we'll move the logical shard around different replica set. And all these can be checked in the same way using that mechanism. Also, with the checksum being recorded somewhere, we'll also be able to verify the consistency of a logical backup. So next I will quickly go through all these different scenarios, explain how we can use the logics for those different types of check. So use case 1, steady state feed-wide consistency within a replica set. So the A side will be one random replica from the replica set, and then the B side will be another replica in the same replica set. So how do we do this at scale? Here we can see 4 horizontal stripes. Each one of them represent a replica set. And then you can see they all have 4 nodes. 1 is primary, 3 other secondaries. So we want to cover all the pairs within 6 days. So in order to cover one single replica set, we need to check 3 pairs. So in total, we need to check 12 pairs. And then in order to cover all replica sets in 6 days, then on average, we'll need to check 2 pairs across the fleet. So one thing was mentioned that because we're running a multi-tenant environment, then you will end up having different instances from different replica set collocated on the same host. But on the other hand, we don't want to exhaust the resource on a physical host. So we need to figure out a mechanism or scheduling logics to be able to evenly spread the load across different hosts while doing the checks and not accumulating too much work for a single physical host to handle within a single day. So we use a pretty simple hash mechanism. First, try to throw the replica set into the candidate bucket. And then once a replica set is selected for the day, we'll then select the pairs for the day for the checks. So here we use a basic modular too, because every cycle will have 2 days, and then each day we'll check 2 replica set. So here, even number of the even index of the odd number of the replica set name will be checked on day 1, and then the even number of replicas that were checked on day 2. So here on the first day, replica set 1 and 3 were picked, and then the replica set number themselves will serve as a offset for picking pairs. So which is why the first replica set start with host, instance 1 and 2 for the first pair, while the replica 3 use instance 3 and 4 for the first run of check. So after first day, we have 2 pairs covered. Similarly, on day 2, the other 2 replica set have 1 pair covered. On day 3, still replica set 1 and 3 should be picked, but then they offset by 1 because this is the second cycle of the check period. So then the other thing was mentioned that consistency is also sort of contagious. So whenever you check one pair and the other pair, as long as they overlap, we can assume that all 3 instances are identical to some extent, assuming there is no sort of short living drift that have happened ever before. But that has already been covered by the live kind of correctness check. So after that, we can safely assume that all 3 instances look the same for replica set 1. Similarly, the third row is also converted to be 3 greens on day 3. So on and so forth. All the rest of the logic is pretty deterministic. And then after day 4, we pretty much cover 2 different pairs for all the replica sets. And then on day 5 and then 6, we cover the rest of the fleet. So that we successfully check all the pairs within the desired period that was configured at the very beginning. So that's what we call parallel check, guarantees data at rest consistencies. We're also doing a lot of instance migration, so therefore the AV side for the migration cases is one side is online data, the other side is the new instance that being migrated to. It can be a different engine or different version. So similarly, we build new engines or new version data from using the online data, but they will start with offline, so they're not taking any production traffic when they're initially built. So we use the same checksum mechanism to establish snapshot and compare checksums to make sure they are consistent before they were put into an online system serving live data. The other interesting usage is backup validation. Because we are doing consistent check every day across the fleet, so we're not actually throwing away all these checksum values to some trash can, but we actually record them in a centralized system together with the GTID that it was observed. So basically, we have backups taken every now and then, every day on this horizontal axis. We also have live data in production that constantly being changed. So the goal here is to somehow check the consistencies for the backup to make sure it has exactly the same logical data with the live data. So to achieve that, we have checksum computed at random point of time in production, recording the system together with GTID. So we know that this checksum existed before, or this state of data exists once upon a time in production before. And then that will be used as a kind of comparison basis, or we call it A side. So the B side will be the backup. So if we can manage to somehow restore the backup up to that particular GTID point, then those 2 sides are comparable. So the way how we achieve that is basically we pick a random backup that goes that dates back to the point before the checksum was completed. We restore it in a database by loading the data into a live masquerade instance. And then because we also back up all the binary logs in the backup system, so we just reapply the binary logs to bring the state of that data forward up to the point where we can have exactly the same GTID set. Then we compute checksum, and then these two checksums expect to be the same. If they're not, then it's a backup corruption issues. Similarly, we're also using this logic to make sure consistency across shard migrations. The idea is also the same. On the left, we have a heavily loaded replica set. On the right hand, we have a relatively idle replica set. So if this yellow shard was picked as a migration target, then it will be moved away from the current replica set to the new one to serve the purpose of load balancing. So first step of the logical migrations will just dump and load the data onto the destination. And then once that is done, the data on the destination side will look stale because there's no streaming of binlog events. While on the other hand, the left hand is still taking live traffic, so the data keeps getting changed. So we'll just pick a random spot, start a transaction, and then capture the snapshot for that particular GTID. And then using that as a comparison basis for consistency check. And then at the top of the migration tool, we'll use binlog replay to fast forward the state of the destination to GTID2 to align the GTID. Then again, compute checksums to ensure that the logical data on the destination side are identical to the source before the final cutovers to ensure shard migration correctness. On top of that, there's also another interesting use cases for version or engine migrations. We not only want to make sure like the data from the new engine version are consistent, but we also want to make sure the behavior of that instance or the new engine are consistent with the old ones. So sometimes there might be query optimizer bugs or executor bugs or engine API bugs that might end up return wrong result for exactly the same sequels across different versions. So to be able to ensure that or prevent that, we introduce a new type of check which is called Correctness, which utilizes similar ideas. On the left hand, we have online system. On the offline side, we have a newly built, freshly built MyRocks instance. Assume we didn't do our job right, introduce a bug in MyRocks. How do we find that the potential kind of query result corruption bug in the MyRocks instance? So the way how we do it is that we capture a snapshot using the same mechanism I just explained before. So we open two transactions, but then the next kind of step was to reapply all the queries to compare to the result. So the way how we do it is that we have a ShadowDB plugin that is built in-house in the Masquerade instance that capture all the select the instance has received into a queuing system. And then on the output side of the queuing system, we have a replayer that replay those select queries against those two different instances within the same consistent snapshot. So the basic expectation would be all the results that were fetched from those two, or the execution result from those select sequels should be the same. If they are not, that means either one of them is wrong, which more like to be MyRocks, because if it's widely used and it's not that frequently changed. So whenever that happens, we look into the query execution engine to see what's wrong with MyRocks implementation. Once we identify the data drift, we also form up the best practice regarding how do we actually root cause the data drift and then fix them, which is also the trickiest part because there's never a consistency issue that is repeated. Every single case is sort of new. We need to sort of reason about it and try to guess where exactly the issue is. Because once you pinpoint the differences, the first hard step was to actually figure out the right copy of data. Because these two rows look different, but it's hard to tell for most of the time which copy is wrong. Sometimes it's very obvious because for bit flipping, you might end up with that JSON that is not deserializable. Then that part is the wrong copy. But for two copies that are kind of reasonable from human perspective, then it's relatively hard to reason about which exact copy was right or wrong. So we will try to find additional information to help with the investigation. For example, if the row comes with a timestamp, then we know the newer ones were likely to be the one that was supposed to be persisted. Or we'll also go through the binlog stream to see from a consecutive events perspective what are the latest version that was supposed to be persisted as a result of replication. So the one with the older version would likely have already missed the newer events as a part of the crash recovery promotions or replication bug. So which is normally, these are the steps that we follow to kind of root cause the data drift issues, which admittedly is the most kind of complicated part for the overall consistency guarantee to be able to root cause every single different cases that we found in production. So right on time, 3 minutes. The most exciting part, war stories. There's a lot of issues that was identified in production. I would just pick two that is sort of representative and fun to read about. One is bit flip. Like I mentioned, bit flip happens every now and then in production in different ways across CPUs, memory, and disks. So here we actually had a case where we have application that's throwing errors in deserializing one particular JSON value in production. And then in some cases, it's still deserializable, but the value looks totally off. Here is the easy case that a human can reason about, because we can see there's some kind of incorrect spelling persisting in the after image. So here we identify that that the one with wrong spelling was the wrong copy. And then we look into that host and then actually perform another round of consistency check for all the instances that it's serving, and found a couple of more cases. And then we narrow this down to a host issue. So isolate the host and then kind of give it back to the vendor for further investigation, and end up finding out this is a CPU bug, which causing random bit flip to be happening in production. The other interesting issue we found is during the 8.0 migrations. It's a particular issue in how redo log was reapplied against the instance that was copied by extra backup. But it's not entirely extra backup bug. It's mostly how we are using extra backup in production. Because we have active schema change every now and then in production live database. So we're not constantly, we're not actually taking the backup block that was introduced in 8.0. So the whole duration of the physical copy was not protected against schema changes. Which is why we historically have been relying on extra backup to error out if there's a conflicting schema change. It wasn't able to replay through for consistency purpose. But in the new 8.0 extra backup, there's a behavior change. Instead of erroring out, it will just constantly create an empty table space and swap in a totally empty table to replace the table that has gone through a schema change. So here's how it happens. We have 3 nodes replication deployment. We try to copy a new, build a new 8.0 instance using extra backup. And then during the whole process, there was a rename table or schema change that happened within the replication, adding a new column to one of the table that is being copied over. Extra backup didn't notice that because the schema change happens after the original table has been copied. So all these were sort of unnoticed, except the fact that the rename table operation was persisting in the read log. So when we're applying the log on the destination side, the crash recovery code noticed that, okay, I'm supposed to run a schema change or 3-way rename to finish the schema change, but I don't actually have the original table copied. So instead of erroring out, it created an empty table space and finished the table swap. So we end up with an instance that have one particular table that has none data in it, which obviously is wrong. So fortunately, we discovered this in a staging environment that we now have better understanding regarding why not taking backup block as a part of physical copy is not a good idea. So we try to work around the issues and then fix the bug so that again, we can erroring out whenever there's schema change colliding with the physical copy. So I think we're on time. the end of the talk. And most important, we are still hiring. You might hear news or rumors regarding like we have hiring freeze, but production engineers are special. So the hiring freeze only impact the software engineers, and we are, yeah, we're critical employees. Well said. Yeah. So if you're interested, hit the link. We're still hiring. And that's the Q&A sections, I guess. Cool. Any question?
Right, Correctness check. What was the motive of developing your own diagnostic of using PTM?
Could you repeat the question?
On the Correctness check, after comparing different results between the two engines. So, what was the motive of developing your own system of using PTM?
So the question is, what's the motivation behind us implementing our own solution for correctness instead of using the Percona toolkit, right? So there isn't too many technical reasons behind. I guess the only reason is because there isn't too many pro experts, I guess, in the company. Well, we're largely using Python, so we want to maintain a technology that nobody understands how to maintain. So we end up writing our own kind of correctness checks. And also we do have lots of kind of weird cases we want to skip. For each case, it's like floating number, which is sort of expect to be different from the result set perspective. So there's a lot of kind of filtering and massage we need to do there for correctness, which is why we think a customized version is more manageable from that perspective. Cool. If no other questions, I guess that's the end of the presentation. Thanks for coming.